welcome you in the lecture series of random processes, detection and estimation. It is 43rd lecture of this series. In the previous lecture, we have discussed risk function, MMSE estimator, map estimator and Bayesian ML estimator. In this lecture, we will discuss linear Bayesian estimator. The outline of this lecture are linear Bayesian estimator, where we will discuss linear minimum mean square error estimator and sequential linear minimum mean square error estimator. And in the objective of this lecture, you will able to explain the linear Bayesian estimator. Now we start with the introduction. The Bayesian estimator discussed previously are difficult to implement in practice as they involve multidimensional integration for the minimum mean square estimator and multidimensional maximization for the map estimator. In general, these estimators are very difficult to drive in closed form except under the jointly Gaussian assumption. Whenever the Gaussian assumption is not valid, an alternative approach is required. In this lecture, we introduce the Bayesian estimator derived with a linearity constraint which depend on only the first two moments of the PDF, and this approach is analogous to the best linear unbiased estimator BLUE in classical estimation case, and these estimators are also termed as Wiener filter. Now first one is linear minimum mean square error estimator. Let the parameter theta is to be estimated based on the data set X, the transpose of X0 X1 to Xn minus 1. Rather than assuming any specific form of the joint PDF P theta X, we consider the linear estimator theta cap is equal to summation n0 to n minus 1 an xn plus an, and it will be equal to A transpose X plus an, where capital A is the transpose of A1 A2 to an minus 1, and here an is the weight coefficient. Now the estimation problem is to choose the weight coefficient an to minimize the Bayesian MSE. So the BMSE theta cap, it will be the expected value of the whole square theta minus theta cap, you know this thing. So it will be expected value of theta minus A transpose X minus an from this, where the expectation is with respect to PDF X theta. And this resultant estimator is termed as linear minimum mean square error estimator. And this LMMSE estimator will be suboptimal unless the MMSE estimator to be linear. The LMMSE estimator is linear when theta and X are jointly Gaussian. So if the Bayesian linear model is applicable, we can write X is equal to H theta plus omega, and the weight coefficient are obtained by taking the differentiation of BMSE theta cap with respect to theta and put it is equal to 0. Then we have an is equal to expected value of theta, and it will be equal to summation n0 to n minus 1 an expected value of xn minus expected value of theta, and it will be equal to A transpose expected value of X. And now A will be the inverse of the covariance matrix CXX and the cross covariance matrix CX theta, where CXX is the n is to n covariance matrix and CX theta is the n is to 1 cross covariance matrix. So the LMMSE estimator is theta cap is equal to A transpose X plus an, and it will be equal to E theta expected value of theta plus the cross covariance C theta X into inverse of covariance CXX into X minus expected value of X. And you know, since C theta X, it will be CX theta transpose. So here they are interchanged, X and theta are interchanged with the transpose. And for 1 is to n vector parameter theta, an equivalent expression for LMMSE estimator is derived as BMSC theta cap, it will be equal to the expected value of theta minus theta cap into transpose of theta minus theta cap, and it will be C theta theta minus C theta x and inverse of C xx into C x theta, where C theta theta is the expected value of theta minus expected value of theta into transpose of theta minus E theta, and it is the P is to P covariance matrix. Now let us take one example. Let xn is equal to 1 plus omega n, where small n is from 0 to n minus 1, and a is the uniform distribution from minus a naught to a naught, and where omega n is the white Gaussian noise with variance sigma square, and a and omega n are independent. Now estimate a. This is DC level in white Gaussian noise with uniform prior PDF. The MMSE estimator cannot be obtained in closed form due to integration required. Now apply the LMMSE estimator. The expected value of A is 0, so this means the expected value of xn is 0, and since expected value of xn is 0, the covariance, it will be Cxx expected value of x transpose, and it will be the expected value of A into 1 matrix of all ones plus omega into transpose of A1 plus omega, and it will be equal to expected value of A square 1 into 1 transpose plus sigma square into identity matrix, and the cross covariance C theta x, it will be the expected value of A x transpose, and it is expected value of A and transpose of A1 plus omega, and it will be equal to expected value of A square into 1 transpose. And you know here one is the n is to 1 vector of all ones. So now from this we can have the estimated value of A cap is equal to the cross covariance matrix C theta x and inverse of the covariance matrix C xx into x, and it will be equal to sigma A square 1 transpose and inverse of the matrix sigma A square 1 transpose plus sigma square into identity matrix and into x. Let sigma A square will be the expected value of A square, and if mu A is 0, mean value of A is 0, then A cap will be sigma A square divided by sigma A square plus sigma square by n, and it into the sample mean x bar. Since sigma A square is expected value of A square, so it will be 2 A naught whole square by 12, and it will be A square by 3. So the LMMSE estimator of A, it will be finally A cap will be A naught square by 3 divided by A naught square by 3 plus sigma square by n into the sample mean x bar. You know the sample mean x bar, it is 1 by n summation n0 to n minus 1 xn. Now consider another example. Consider the acoustic echo cancellation problem. The purpose is to show that variance of the estimator of the echo path impulse response could be lowered further by dropping the unbiasedness constraint. The signal flow diagram is, you can see in this figure, and then find the LMMSE here, and this is the loudspeaker, and this is the microphone, and this is near end signal, and this is to far end, and this is from far end. So this is the acoustic echo path, and the output vector at the microphone, it can be expressed as y is equal to UH plus V. Let us assume that the echo path impulse response is a random variable H naught with some prior knowledge, means with the PDF P H naught has first and second moment S. So we have considered the prior knowledge of PDF, and it is having first and second moment as mu naught is equal to expected value of H naught, and P naught is the covariance of H naught. So we have the mean value mu naught and covariance P naught here, and the covariance, it will be the expected value of H naught minus expected value of H naught into the transpose of H naught minus expected value of H naught. Any linear estimator H cap is equal to A is to the power A transpose Y. Maximizing the Bayesian MSE means B MSE H cap, it will be the expected value of H cap minus H naught into transpose of H cap minus H naught, where H naught denote the true value of the impulse response is given by the mean of the post RPDE P H naught by Y. So the H cap LMMSE linear minimum mean square estimator, it will be the inverse of the matrix mu naught plus U transpose R inverse U plus P naught into U transpose R inverse into Y minus U mu naught. If the prior knowledge is constrained as mu naught is equal to 0, then H cap LMMSE, it will be equal to inverse of the matrix U transpose R inverse U plus P naught into U transpose R inverse Y. And if you find out the blue best linear unbiased estimation, the blue will be equal to inverse of the matrix U transpose R inverse U and into U transpose R inverse Y. So the MMSE criteria for the Bayesian framework, the variance of the estimator and the squared base are weighted equally. So the variance of the estimator could be reduced further than that of the MVUE if the estimator is no longer constrained to be unbiased. Now another is the sequential LMMSE estimator. We know that the LMMSE estimator A cap n minus 1, it is equal to summation sigma A square divided by sigma A square plus n square sigma square n into the sample mean x bar, and also BMSE A cap n minus 1, it is sigma A square by n sigma A square plus sigma square. To update our estimator as xn, it will become A cap n, it will be equal to sigma A square divided by sigma A square plus sigma square by n plus 1 into 1 by n plus 1 summation n0 to n minus 1 xn, and it will be equal to A cap n minus 1 plus sigma A square by n plus 1 sigma A square plus sigma square into xn minus A cap n minus 1. And this part is the scaling or gain factor Kn. So the scaling or gain factor Kn is sigma A square divided by n plus 1 sigma A square plus sigma square, and it will be equal to BMSE A cap n minus 1 divided by BMSE A cap n minus 1 plus sigma square, and it decreases to 0 as n tends to infinity. So BMSE A cap n, it is sigma A square divided by n plus 1 sigma square by plus sigma square, and it will be, you can write as 1 minus Kn scaling factor or gain factor into BMSE A cap n minus 1. So the estimator update, it will be A cap n, it is equal to A cap n minus 1 plus Kn into xn minus A cap n minus 1, where Kn is BMSE A cap n minus 1 divided by BMSE A cap n minus 1 plus sigma square. And the minimum MSE update BMSE, it will be A cap n, it is equal to 1 minus Kn BMSE into A cap n minus 1. Here so far in this lecture we have discussed linear MMSE estimation and sequential LMMSE estimation. This was 43rd lecture of the lecture series of random processes detection and estimation. In the next lecture we will discuss about Wiener smoother. Till then, thanks for listening to this lecture. Thank you.